Previously on Physicsball Z, our heroes returned to the powerful equations that can be used to calculate these mathematical monstrosities. And they discovered the main mechanism that generates electricity in power stations. And from all the information that they gained, they were able to explain why electricity is transported at high potential differences. And now, for our heroes to defeat this new threat, they must tap into the internal energy contained in the kinetic molecules. Will our heroes change the state of affairs, or will the latent heat be too hard to handle? Find out in today's episode of Physicsball Z. Here are the retrieval questions for this lesson. You know what to do. Step-up transformers increase the potential difference across transmission cables. This reduces the energy wasted. Turbines in coal power stations turn due to high pressure steam. Endothermic reactions absorb energy. Exothermic reactions release energy. Ionic bonds are electrostatic forces between oppositely charged ions. Covalent bonds are shared pairs of electrons. Just a quick reminder of some of the information from Chemistry 1. Atoms are made up of positively charged protons, neutral neutrons, and negative electrons. Atoms are made up of these charged particles, so why then do atoms not have an overall charge? See if you can answer this question. The number of positive protons and negative electrons cancel each other out, and that means the overall atom is neutral. We have three states of matter that we're going to discuss in this lesson. So you can either mentally imagine what these particles look like, or you can get a pen and paper and draw this out. Solids should be drawn with the atoms touching, and they should be in a regular arrangement like this. The only motion that they can exhibit is that they vibrate in a fixed position. Liquids, on the other hand, is where people flop. All the particles still need to be touching, but they can slide over each other randomly, and they're not in a regular arrangement like solids. Gases are the ones that are not touching when you draw them out, and that's because they move rapidly in all directions. See if you can answer these challenge questions here. The state of matter with the least amount of energy is solids, and the type of energy that they have is kinetic energy. This image shows a container of gas and a red dust particle. If you were to look at this dust suspended in a fluid, it looks like it's moving randomly around. This is called Brownian motion, and this was one of the evidence that we had for the existence of atoms. Because we couldn't see the air particles, we can't see the water particles, but we could see the dust, and it looked like it was moving randomly. The bottom images show two boxes that have a pressure gauge connected to them. And just to help you out here a bit more, you can think of an individual gas particle like this fist hitting the walls of a container. Here I have some challenge questions for you to have a go at. Do your thing. If you heat up a substance, the particles will move around faster. Gas pressure is caused by the gas particles colliding with the walls of the container, so it's almost like they're punching the walls of the container. Now, based on all what we've seen so far, the hotter gases collide with the container more, which means that the pressure must be higher. And looking at the pressure valve, A has a higher pressure, so that must contain the hotter gas. Internal energy is the amount of energy stored in the particles in a substance. And we've already seen kinetic energy, which is due to the motion of the particles, but there's another. This is potential energy, which is due to the positions of the individual particles. You could be asked the effect of heating on the internal energy of the particles. Heating a substance can increase the internal energy to the point where the substance can change state. Here I have the different states of matter that we saw before, and we've got 6 different state changes of matter. See if you can complete this table based on the letters on the diagram. A is a liquid going into a gas, so that's boiling. B is a gas going into a liquid, so that's condensation. C is freezing. D is a solid going back into a liquid, so that's melting. E is a solid going into a gas, we call that sublimation, which means that a gas turning into a solid is deposition. On Earth, water can exist as a solid, liquid and gas on the surface. If we plot a time versus temperature graph as we heat ice all the way to steam, we expect to see this straight line. Notice that we start below 0 degrees Celsius because we start off as ice. But this is actually what the line looks like, and it's called a heat curve. The main thing to notice here are these horizontal lines. Let me get Jaden to help us out here. Jaden, what do these lines represent? What's important about those two temperatures?
Oh, that's when it melts and it boils.
Exactly. Now we're ready for some challenge questions, of course. I've added some numbers here to the diagonal lines 1, 2 and 3 over here. Do your thing. The temperature is lower than 0 degrees here, so 1 should be solid. 2 is in between 0 and 100, so that should be liquid. And 3 is higher than 100, so that must be a gas. When the state of matter is changing from a solid to a liquid or from a liquid to a gas, the temperature is staying the same, it's horizontal. We saw intermolecular forces in chemistry, and when a solid melts, it's these intermolecular forces that break. Remember, it's not the covalent bonds. And the energy needed to break these intermolecular forces is called the latent heat. If you do get an extended answer question based on heat curves of water, you will need some key pieces of detail to collect all of the marks. This challenge question here is asking you to match up the numbers on the graph. Now we've got 1, 2, 3, 4 here to the correct statements. See if you can work that out. For 1, the temperature increases until it reaches 0. At 2, the temperature remains constant as the ice melts. This is because energy is not used to increase the temperature but to break the intermolecular forces between the molecules. 3, the temperature increases until it reaches 100 degrees. And therefore the temperature remains constant as the water boils, which again is caused by breaking the forces between the molecules. That is 4. The specific latent heat of fusion is the energy needed to change 1 kilogram of a substance from a solid to a liquid at the melting point. Latent means hidden, and this is because this energy that we add doesn't register as a temperature change. Remember, the temperature remains constant when a substance changes its state. So it's latent, it's hidden, we don't see a temperature change. I've got these challenge questions, of course. Do your thing. Specific latent heat of fusion is the energy in joules over the mass in kilograms. Looking at the equation, the unit must be joules per kilogram. To rearrange this to work out energy, we need to multiply the specific latent heat of fusion by the mass. The specific latent heat of vaporization is the energy needed to change 1 kilogram of a substance from its liquid to its vapor at its boiling point. And just like before, I've got these challenge questions for you to have a go at. Do your thing. Specific latent heat of vaporization is energy over mass. The units like before is joules over kilogram. And to work out energy just like before, it will be the specific latent heat of vaporization times the mass. Now based on all that we've done, see if you can answer these quick check questions. We need to work out the specific latent heat, and we've got 50 joules and 100 kilograms. This gives you 0.5 joules per kilogram. The rest of the answers will look like this. Notice that we had to convert the kilojoules into joules and the grams into kilograms over here and over here. For this last activity, I've got the whole cycle of state changes here, but I've also included what happens to the latent heat at each stage. You should know what to do when you get these type of questions. When something's melting, we see that it's absorbing the latent heat of fusion. The two processes that release energies into the surroundings are freezing, or solidification, and condensation. Finally, if melting and boiling break forces between particles, those intermolecular forces, that must mean that condensation and freezing must make those forces between the molecules. And there we go. Mission complete. Fatality. Check the descriptions, timestamps, all of that. I'll catch you guys in a bit.